Yes. We're live. Okay.
Yeah, I got one. Or do I? I can maybe give you this one. So, can you pass it back to Zach, please? Okay, like I said before, hopefully you're done through 24. Are there any big questions on anything from 1 through 24, where you're pretty much just setting up F net equals MA, solving for some unknown? Anyone else? Okay. Maybe talk to me individually if you're stuck on one. But they should be fairly straightforward. Just follow that process, like I talked about last week, where you're looking for a force diagram. Somehow can you get F net equals MA set up, and then solve for the unknown. So 25 through 28 are all kind of similar questions. Let's look at this stuntman. So 25 says you got all right. Here's the stuntman. He just jumped off a tower. Okay. He jumps off the tower, and just before he hits this foam pad, he is traveling. So I'm going to call this V initial, because the event that we're concerned with is him hitting the pad. We're not really concerned with this event, him falling through the air, right? So because we're ultimately asking, what was the magnitude of the force exerted on the stuntman by the cushion? So let's take the information they're giving us. We know his mass. So his mass is 70 kilograms. We know his initial velocity just before he hits the cushion. He's going 20 meters per second. By the way, you can extrapolate on this. Can anyone tell me roughly how long was he falling? Roughly. Yeah, exactly. About 2 seconds. So you drop something. If you drop it from rest, it gains roughly 10 meters per second of speed every second. So, so just before he hits the cushion, he's going that fast. And of course, how fast is he going, like, after the cushion has stopped him? It's going 0. So that's what a cushion does in this scenario. It takes you from an initial velocity of, say, 20, and it stops you. It gets you to rest. And maybe we had a high-speed camera or something, or some kind of sensor that told us that this event, him going from this speed to this speed, took a time of 400. What does that little m mean? Milliseconds. So this would be 400 thousandths of a second. So divide by 1,000. It's 0.4 seconds. So are we all okay with that?
Yes.
Strings. So, what can we do? What can we get? So I've listed out all the information they've given us. What's an extra piece of information that I might want to know about that I could calculate pretty easily from this? Acceleration, right? So if I know a change in velocity was 20, and I know how long it took, that'll give me the acceleration, right? So acceleration is the change in velocity over the change in time. So in this case, we'd have a change of 20 meters per second over a time period of 0.4, which is 50. Cool beans? So now here's where it gets kind of interesting, because a lot of people here would want to just go, okay, well, m times a, which you can do, but you got to be careful of what that's giving you. Does m times a, well, someone tell me, what does m times a tell you? What quantity? Close. The net force. That gives you the net force. Now, why am I so particular about that? Well, like, look at me standing here. What's the net force on me? 0. But how much force is the floor exerting on my feet? That's, well, mg, whatever my m is times g. So if I'm not 100 kilograms, maybe. So if I were 100 kilograms, then it'd be 9,800 newtons of force. Or sorry, did I say that wrong? 980. Sorry, I said that wrong. By the way, a kilogram on Earth, so just in case you guys didn't know this. If I have a 1 kilogram weight, I got some over here. So, in case you haven't seen these before, like this is a kilogram of like brass or something, whatever this is. So 1 kilogram, the weight of a 1 kilogram weight on Earth is 2.2 pounds. How many of you guys are already familiar with that? So, if you watch like any professional sports that are like covered in Europe, they'll tell you the athletes' weights in kilograms, not pounds. Anyway, so now, but of course, keep in mind, it's a little weird though because that's a mass and that's a weight, so it's not the same. What it means is though on Earth, so on Earth, this has a force of 9.8 newtons. So really, the equivalent is 9.8 newtons is 2.2 pounds. So if you want to be really like actually on someone goes, oh, a kilogram is the same as 2.2 pounds. You go, well, actually, a kilogram is a measurement of mass, not weight. So then you can be really popular at the party. What?
I said everybody will love you.
Yeah, everyone will love you. Everyone will be like, wow, thank you for telling me that. Yes, I'm so enlightened. Okay, so anyway. What we could calculate right now is we could say, well, I got this really famous formula. They tell us that this is like one of the most famous formulas ever. So if I plug into this, my mass is 70, my acceleration is 50. So that's 3,500 newtons. Cool beans? But the question is asking not what's the net force, it's what was the force. By the way, the word magnitude just means size. So, it just means technically a force is a vector, it has direction and magnitude. So the magnitude is just what's the size of that vector, okay? So what we gotta do, and this is what I was talking about a moment ago. Like when I'm standing here on Earth, on the floor here, the net force is 0, but that doesn't mean the floor isn't exerting force on me, right? So there's a difference between net force and how much force is the thing exerting on the object. So let's look at the force diagram. Here's the guy. This block represents the dude. Or should I just make a mistake figure? I don't know. Let's make a mistake figure. I'll draw him like this. There he is. Okay. There's 2 forces. Again, what's the event we're talking about? Hitting the mat. That's the event. If we watched it in slow motion, the clock would start when he first makes contact with the mat, and the clock would stop when he's finally at rest. So how much force is pulling him down? It's the gravity force, mg. So the force of gravity, mg, would be 70 times 9.8. Mr. Quackalator, what is 70 times 9.8? 686 newtons. And then what is the force from the mat, or the pad, or whatever? What do we call it? Mat or pad? Doesn't matter really. Cushion. The force from the cushion or the mat, whatever you want to call it. Now, do you guys see what's going to happen here? Is it clear or no? What do I have to do now? Well, obviously the net force has to point against his motion. He was traveling this way, so in order to slow him down, the net force has to point the other way. And so I can say, well, Yeah, so that net force, if I look at the diagram, the net force was the mat force minus the 686. So I actually end up having to add that 686 over. All right. And is there a confusion on that? Does everyone understand how I can replace F net with the subtraction of those two? Does that make sense intuitively? Okay. Also, perhaps more important than the calculation is just the general idea of like, when I'm standing here, let's say I'm this guy, 70 kilograms, that's actually, it's like 150 pounds. Something like that. So, right, let's say I'm this guy. Well, just standing here still, that's how much force is exerted on me by the pad, right? So in order for the pad to accelerate me, to like slow me down, it has to exert, it's starting there. That's like the baseline number. That's just to keep me sitting there. So it's got to go beyond, that's the net force you need to cause that acceleration, right? Where is our acceleration? 50. In order to generate that much acceleration, you need that much net force. Well, to generate that much net force, you have to exceed my weight by that much. Does that make sense? A little bit? Okay, so by the way, if you've ever, I'm sure as a kid, maybe you like bounce on a bathroom scale, like stand at a bathroom scale, it'll tell you, okay, that's how many pounds I am. And if you kind of like, kind of jump on it a bit, like make it, kind of like it's a mini scenario of this. You'll see the needle go up, right? Because it has to increase the amount of weight that to hold you up and just to slow you down when you jump on it. Okay. All right, try 26 on your own. And then we'll do 27 together because that one's a little bit weird. You are the best. So have you guys noticed on this problem that something is required? Something. What number would we like to know Yes, exactly. We'd love to know what was the velocity just before it hit the pad. I have to dig deep into our mind palaces. Is there some way where I can pretty directly get from the height of a tower for a dropped projectile, how fast is it going at the bottom of the tower? What's that relationship that we derived before? Does anyone remember it?
Yes.
Dropped ball. The relationship was, well, this is one way to write it. I could use the time in. So let's say I'm always going back to like first principles on every problem. Say on every problem I have to go back to like one of the big famous formulas. Where I'd start would be this. I'd go back to this one, the famous time independent. And do you see how if you make this 0 and you make the acceleration g and the displacement would be the height of the building, and then if you solve that, you get this. Yes, no, maybe so?
Yep.
And then you can rearrange this, move the 2g up here, and square root. Everyone cool with that too, or? Yeah? Okay, so let's take that and let us figure out what this velocity is here. So the velocity when he's right here would be the square root of 2 times 9.8 times, what's the height of the building? 40. Oh, great. Calculator. What is the square root of 9.8 times 80? Oh, no, not that. Helps if you type it in correctly. Turns out it's exactly 28. It's pretty neato. Why is that? What? Well, because 98 is double 49. So 9.8 is 49 over, sorry, times 2. Oh, divided by 10, sorry. There's a 2 in there and a 40. Oh, so that makes a 4. Okay. So there you go. 2 times 2 times 2 times 2 times 7 times 7. Isn't that neato? Oh, man. Fascinating. No? No? I just thought it was, I don't know. I didn't expect to get an integer out of that. Surprising. What? What I was saying is it's curious. Usually when you type a decimal into a square root, typically when you square root a number, odds are it's going to shoot out a decimal, right? So I was just thinking it was interesting why this comes out to be exactly 28. And the reason is 9.8 is double 40. Okay, 9.8 is 49 times 2. That makes 98, right? So divide it by 10 to make it, so that number right there is 9.8. And then there's a 2 there, right? And there's a 40 there. 40 is 4 times 10, right? So you agree that, so that's all under a square root. So the 10s cancel. And so now what I have is 4 times 4, whose square root is 4, and 7 times 7, whose square root is 7. 4 times 7 is 28. It has nothing to do with physics. I just thought it was interesting. I'm sorry. I just thought it was neat.
I just got lost for a minute here when you made the 9.8, the 2 times 49.
Sorry. That's my bad. But yeah, so yeah, because I was wondering, like, how do you get a perfect square out of 9.8? But yeah, it's double 7 squared over 10. And the 10 cancels out that 10. So where were we? Sorry, I'm off topic here. Okay, so that now we've reduced it. Big thing in math and physics and et cetera is you've taken a problem and you've reduced it down to a problem you've already solved, right? So we've basically already just solved this problem where I know the speed of my object just before it hits the pad, right? Is I have this number. Same process, right? So do I know the delta t for this one? What's the delta t? 80 milliseconds. So I have to go 80 divided by 1,000. Okay. Remember, you always have a calculator, so if you're still not getting the whole dividing by powers of 10 thing, well, I would still recommend trying to learn it. You're moving it 3 spots, 1, 2, 3. But in any case, you can use a calculator if you're stuck. Okay, so my acceleration. Sorry, these markers, man. All right, heads up, Lindsay. I'm gonna make it this time. It's going in. That's close on that one. So the acceleration is the change in velocity. So the change in velocity is 28 because he's going from 28 to 0. The delta t is 0.08. What's that going to be? 350. That's a lot of acceleration. What does that mean, man? What does he say when he saws the boat in half? That's a lot of damage. That's what it was. Sorry. That's a lot of damage.
When he saws the boat in half, he says, I sawed this boat in half.
Oh, when does he say that's a lot of damage?
That's a lot of damage. It's classic.
Okay, so now with that, you can calculate the net force. So the net force is going to be the mass times the acceleration. So you multiply that. What was the mass? Okay, so what does that end up being? 75 with a 0. Newtons. Now here's one where how much force does gravity exert on this ball? Huh? Say 50? Yeah, it's 50. 50 is a good estimate. No, 50's fine. 49 newtons. How does 49 compare to this number? It's just a wee lad. But it's still, I mean, we're still going to count it. So here's the ball. So at that moment, as the pad is slowing it down, as it's hitting that cushion, there's 49 newtons pulling him down, and there's some unknown, the force from the mat, is pushing him up. Now this minus this has to equal this. So algebraically speaking, I would just replace this F net expression with F mat minus 49 and get my answer. So you get 1799? How do we feel about that? Does that all make sense?
Pretty cool.
Okay. So, all right, once you guys, so 27, I think you guys can, you might get stuck at a certain point, but this is a big hint. This thing right here is going to help you out big time on 27, but I want to make sure the question is clearly stated. So Stuntman Bob is going to be shot out of a cannon aimed horizontally. Okay, so what that looks like is, here's the ground, here's the human cannon, here's the pad. Okay, we're going to shoot him out of the cannon, just straight into the pad pretty much. Okay, now I'm saying you can ignore gravity because the gravity vector points down, so technically if you want to be really precise, would you have to account for that vector? Yeah, but we're going to shoot him out of the cannon pretty fast, so we're really just concerned with the horizontal forces here. So this problem is actually going to be slightly easier because you're not going to have to really think about two opposing forces, right? If we get to ignore gravity, then once he's hitting the pad, what direction is the only force exerted on him? the cushion pushes him that way, right? He's traveling this way. The force pushes him that way to slow him down. So now you'll notice when you read this, it says, oh, Bob's 80 kilograms. We know that he can withstand 4,000 newtons of force. 4,001, he explodes. 4,000, he's good. So we know that we can shoot him out of there. So what are we ultimately solving for? Hint, hint. Now we know his initial velocity is 25. Right? When he first strikes the pad, when he first makes contact, his velocity is 25. What's his final velocity after the pad is stopped at 0? So we know V initial, we know V final. We could figure out the time. That's actually one way to do this. Well, when the pad is going to compress, right? That's a displacement, right? That's a change in position. So what we're going to look at is, in order to go from 25 to 0, we can calculate his acceleration because we know the net force on him, assuming he's going, right? Assuming we're pushing him to the limits, his physical limits, 4,000 newtons. We're going to give him the full 4,000 newtons, and we know his mass is 80, so we can calculate the acceleration. We can say, so for Bob, we can either say Bob can take up to 4,000 newtons, or we might say Bob can handle up to, what would that end up being? Is it 50? Or is it 500? No, it's 50.
Yeah.
We could say Bob can withstand 50 meters per second squared of acceleration. Does that make sense when I'm getting that number? F equals ma? So then once you have all that, you can solve for what's the displacement over which that event can take place without crushing his bones. Okay. You'll notice that if you decrease, so if these numbers are set in advance, so 25 and 0, what happens if you make this number small? This number has to get big, right? If this is a constant, if this number is set, these numbers are multiplied together. So if this number gets small, this number gets big. In other words, thin pad is going to be hurdy-hurdy, right? If you get shot out of a cannon and the pad only has this much space to compress, right? A small displacement, that's going to be a very large acceleration on your bones, right? Conversely, right, in real life, you guys have seen a safety net before, right? A safety net lets you slow down over a very large distance, right? So that would decrease the acceleration. That's the whole science, or that's not the whole science, but it's the main idea behind like crumple zone on a car. You guys ever heard of those?
Yes.
So like in the old days, they used to be like, oh, this car is made of solid steel. But that's a problem because like, well, one, it's all the jaggedness, but if you hit a wall, right, and this frame doesn't like bend at all, then this number is really small, right? You're going from high speed to low speed extremely over a very short distance. But if the car can like crumple up and this whole thing can collapse, then it essentially absorbs. There's a lot of ways you can think about it. It absorbs the energy, or you can talk about how it's actually increasing this distance over which this acceleration takes place. Or you can think of it in terms of it's increasing the time over which the crash takes place. Big acceleration, big delta t, smaller accelerations. Anyway, I'll shut up. Try to calculate it. We can check our answer in a second. And then I want to end on talking about one of these string questions, which are essentially the same questions, just to make sure there's no confusion. Okay, did we get 6.25 meters? Thick.
Yeah, but it's a huge map.
Yeah.
You're like,
Yeah, that's obviously an enormous. There's a few things going on there. One, I feel like 25 meters per second is pretty fast to handle that with a mat. Would probably not be practical. Like if you ever seen a trapeze artist, their safety net is this huge. I mean, it's like a huge net that's like on elastic cables and stuff, where the person hits they hit the net, and they have like, I mean, it could be 100 feet of give. Does that make sense? You guys have seen that before, right?
Yeah.
Okay, so yeah, so if you're talking about falling off a big trapeze thingy, then you're going to need a lot of distance to spread that acceleration over. So yeah, 25 meters per second is pretty fast. I mean, that's pretty fast. So okay, let's talk about. So I'll save 28 for you. It's the same principle. You can set it up exactly the same way, pretty much. I believe 28, you'll notice on 28, it's about shooting a projectile into a block of ballistic gel. And a sort of an instrument tells us the force that was exerted on the projectile by the block. And they also tell us the time. So when they tell you the time, you probably don't need to involve the time-independent equation. So this one might be more akin to like 26 or 25. So, okay, one of the last things. This might be relevant to the, are any of you guys fisher people? Julie, I know you fish, right? Okay. I don't know anything about fishing really, but I do know that they sell different types of string or whatever, fishing line. Okay. And tell me if I'm wrong here. Like if you got a 10-pound line, that means it's designed for a fish that's like less than 10 pounds, right? Yeah. Okay. So if you had a 10-pound line and the fish was like 10 pounds, and then you yanked on the string really hard, you might snap the string, right? The line, sorry, the fishing line. Yeah, sorry. Actually, that's the idea, right? Now, I'm sure in practice, a 10-pound line can actually hold like a 12 or 13-pound fish. Probably won't break. But the idea is, all I'm talking about is the idea is like, yeah, you can have something stable on the line, but once you try to accelerate it, once you try to exert extra force, you can snap the line. So that's basically what these problems are going to be about. Is like some of them will say, oh, this rope is designed to withstand up to this much tension, or what's the actual tension in the string? So let's look at 29 together. While I'm erasing this, why don't you draw the force diagram for 29? It's talking about a 6-kilogram block hanging at rest from a string. So 6-kilogram fish would be what? Roughly 15 pounds, 14 pounds.
Yeah.
Is that pretty big?
Nice.
Is it?
Yeah.
Yeah, it's decent size.
That's not big, is it? I only fish for like a marlin, so with my harpoon. Yeah,
There's no way.
my harpoon.
No. If you caught a 20-pound right, we need to be like this big.
I caught a 30-pounder, so.
You know, we should coach Jones is the in-house fish rep.
Okay. Here's Mr. Fishy after Julia has mercilessly ripped him out of the ocean from his family or the river, whatever. Okay. Never to see his children again. Okay. So he's hanging from a string. Okay. So here's a string. So let's do, I've been seeing these new memes that are really stupid. It's like how it started, how it ended or something. Have you guys seen these memes? Yeah. It's like this, I really don't understand the purpose of them, but anyway, I'll do that here. It's how it started. How it started. What's the end of it? It's how it started and what's the last part? How it ended? I know it's not how it ended. It's something else. I can't remember though. No one can tell me the answer to that? No. Yeah, it's always like, I don't even know. They're always really dumb. Anyway, how it started is he was hanging at rest. So he was at rest before. Okay. So he's 6 kilograms. So how much force is pulling him down?
How it's going.
Yeah.
How it's going. That's what it was. Yes, thank you. How it's going. That's totally right. Okay. Okay, how it started. So, 6 kilograms means, what's that, 50? Help me out here, 58.8. Okay, and then what's the string doing then, if he's at rest? 58.8. Cool beans? No questions there, right? Now, here's what happens though. It says that over a period of 2 seconds, so over a delta t of 2 seconds, he is pulled up by the string, okay? Did gravity change? Gravity does not care, okay? But this tension, the force due to tension, did increase. We don't know what it was necessarily. We don't know what it is yet. But we know that over this period, the velocity, the initial velocity was 0 and the final velocity was 10. So what does that information combined tell us? The acceleration was 5 meters per second per second. Everyone okay with that? So if you got your fish on your line and you pull up to a 10 meter per second speed over a 2 second period, I'm not sure how that would work with just your arms, but maybe on some kind of like a winch connected to you. When I fish, I'm only fishing for marlin, so we have this huge cannon, you know, with harpoon or whales. Sorry, I only fish for whales. That's what it is. Blue whales only. Okay, so anyway, everyone's okay with that, right? So what's our famous equation? F net equals ma. Right? Can I write an expression for F net? Let's do all replacements. In terms of this diagram, what's F net can be represented like?
FT minus the T, right?
Exactly. The tension minus the gravity force. We're okay with that? The mass was 6. The acceleration was 5. Now this answer should, I hope, make a lot of sense because how much tension's in the string? Well, it's how much you started with, the 58.8, that was just keeping it there, plus an additional 30. What was that 30 doing? Well, the 30 was causing the acceleration. Okay? So the force due to tension would have been 88.8 newtons. Cool beans? All right, so are there any questions on that? Okay, so now this could be a, yes. It's 6 times 5. Because the fish was, or the object was 6 kilograms and his acceleration was 5 meters per second squared.
Oh, okay.
Make sense?
Yeah.
So now any question like this, guys, the framework is the same. So there's like, I think there's like 6 of these or 5 of them. Basically, so what happens instead if the problem tells you, oh, this string is designed to withstand up to 400 newtons of tension? Well, you can just set this to 400. Say, assume I'm pushing this string to its maximum tension. Then maybe I can calculate the acceleration, or I can calculate, well, I guess if they give you the acceleration, that you could maybe figure out the mass if you needed to. But that makes sense, how you could then figure out anything else you wanted. Alrighty, the end. They all lived happily ever after. How it started,